My name is Hazim Gaber, and this is part 2 of a structured cabling systems course. So today, we're going to look at twisted pair cabling. We talked yesterday about what we call electric factors, transmission factors, dielectric constants, dissipation factors. Now, I'm going to focus on twisted pair cabling because that's the most common type of cable that we install for data transmission. And if you look on the right, we have a Cat5e or Cat6 cable, and we've got 4 pairs of wires, and one is green, and one is brown, one's orange, and one's blue, as far as the insulation goes. And every 2 wires are twisted together. And they're twisted together at a different rate. And the reason we do that is because we don't want to have noise. If we have 4 pairs of wires and they're all straight, the signal is flowing, let's say, this way and this way, this way, this way, this way, this way, this way, this way. It'll start to bleed between the wires. And also, we've got external, magnetic fields. So we might have a light bulb, for example. Can't draw a light bulb, but we have a light bulb which is giving off light, and light is basically radiation. So it's excited photons, and one of them might hit the wire, and now we've got some noise. So noise is bad because it makes our signal lousy. And then we have errors. And if we keep getting errors, we have to keep resending the data if we can. So a complicated word for this is capacitance unbalance. So we apply a voltage onto one wire and we see a difference in the voltage on another wire, then we know we've got some bleed, and we call that crosstalk. Which is really bad. So if I install a really high-end cabling system, I'm going to test with an automatic machine for crosstalk, because I want to make sure that this system performs to the standards that are specified. I'm going to test for a lot of other things, and we'll get into that later. But basically, if we have nice uniform twists in our wire, we won't have very much crosstalk. So in a phone cable like a Cat3 cable, the pairs will have very low, very wide twists. In a category 5e or 6 or 6a cable, we will have really tight twists. Now, I'm going to stop here. I'm going to look at bonded pair technology. This is not an endorsement of Belden. I do buy a lot of Belden cable, but Belden came up with this thing that they call bonded pair. And what bonded pair does is every pair, they're not just twisted together, but they're also glued together. Now, with a non-bonded pair, I think this photo is probably an exaggeration on the left, but according to Belden, when you have twists and when you're pulling the wire through the through a ceiling space or a conduit or whatever, and you start to strain the cable, the twists start to come out of shape, and then they're more susceptible to noise. So some places really like the bonded pair, especially if you bend a non-bonded pair, you might have some gaps. In this case, you can't have gaps when you bend it because it's completely glued together. They do sell it as patch cables as well, which have a very low return loss, and we're going to cover return loss later. But basically, the Belden bonded pair, it's much easier. You don't have to worry about damage to the twists when you install the cable, and so might be something to think about. It's also a little bit more difficult to install. One of the things that they measured was creating a service loop with a bonded pair cable and then uncoiling it and see if there's a return loss. And they found quite a large return loss on some of the cabling systems, but not on theirs. So, going back to that, we talked about noise, and we mentioned this term electromagnetic interference, or EMI. And we're going to go into more detail about that later. But basically, any kind of electrical or light creates energy in the air. So if I have a room and I have lights in the ceiling, those lights are giving off photons, and the photons are basically little bits of energy, and if they hit my cable at the right spot, then my wire in my cable is going to absorb the energy, and we're going to end up with noise. So the signal that I sent is not going to be the same as the signal that I receive. We also have temperature. So we have a really high temperature, then our wire will gain energy from the surroundings. So if we have a wall or the sun or a heating duct, the cable tends to absorb the heat, and it'll make the cable softer, but it'll also add energy to the cable, and I mean to the wire, and the energy becomes noise. And because all the energy has to go somewhere. So when we think about it, when we come up with our cabling standards, we're assuming a cable in our room or 20 degrees Celsius. When we design our system, we need to think about the current sources of energy and the future sources of energy, and we need to install our cable in places where it's not going to be affected by them. Or if we can't, then we need to think about um, using a higher performing cable or some kind of insulation or something to protect against the issues. So we've got different types of insulation. So if we look at signal loss in decibels, we think about it, PVC performs the worst, and FEP performs the best. That's fluorinated ethylene polypropylene. You know, this isn't really too important, but just know that this is basically Teflon. That's a brand. So yeah, Teflon type of cable jacket is going to protect us a lot better than your standard PVC. So on the left we have a cable that's not shielded, and in the middle we have a cable where the entire core is shielded but the individual wires are not. And then on the right we have a cable where each individual pair is shielded. And we can have a situation where we have a shield for each wire pair and then another shield for the entire cable. So the shield can be braided or it can be solid. It can be made of, it's typically made of foil. The different materials include copper and aluminum. And you can see in this cable we also have a drain wire, which can be used to connect the cable to a ground. So when we have a light bulb or whatever causing our radiation, the PVC material doesn't help us very much, whereas the shielded cable does. So shielded cable is really good when we can't afford any noise or where we want this cable to perform better than what the stated characteristics are. So for example, if I'm doing HDMI over Cat6, so let's say I have a TV and I have a media player and I want to send my data over an extender. So these media players, they're much more susceptible to noise than your standard Ethernet. So this part's HDMI in, this is HDMI out, this is Cat6. So I might put a shielded Cat6. And we can measure the shield by what we call impedance. And it's in milli ohms milli per meter cable. So we're asking how much noise can this protect us from? So really the best type of shield is a big solid conduit made of metal. But conduit's not always possible. It's expensive. We may want to run our cable free air, and we may not have much noise. So conduit's not always the best. And conduit's solid, so we gotta get an electrician or somebody to come in, install conduit, bend the conduit. You know, getting conduit all the way down an existing drywall, for example, is not practical. So yeah, we should think about what are we sending, what kind of data, what's the frequency, and then what are our sources of radiation and how large are they, and other types of requirements like mechanically, can we use a conduit? So we've got, if we want to compare the best type of shield is a solid conduit, also known as EMT. And then we have a flexible metal. This is metal conduit. We sometimes need flex because we might have a ceiling space where we can't fit a solid conduit. So this is kind of like a hose. It's a metal hose. And then we have a foil plus a braid in the cable. And then we have a multiple layer braid. We have a single layer. These are also in the cable. So we can probably do 60 dB here and maybe 40 dB. $20 to $40, maybe even $60. Now you might be working on a project that requires conduit. For example, train station. We did a project that all the cable had to be in conduit, but it was new construction, so it wasn't so bad. And then I mentioned the drain wire. So what we want to do with the drain wire, because the drain wire connects to the shield, is we need to ground that drain wire, because the electron hits the shield and it travels out through the drain wire and then into the earth. So you want to make sure your drain wire is made of solid copper or stranded, but it's gotta be copper. And that's where we stop. Any questions?